So critical points happen at those two situations. The domain of a function is a critical point if either the derivative is 0, yay! Or, yeah, we could say it's infinite, or it does not exist. Okay? 0, get a visual picture of this.
Pillar valley.
0 critical point means horizontal tangent line, right? So we're talking about hills and valleys. Okay, infinity or does not exist means a vertical tangent line, right? Corner or cusp. I should say either vertical tangent line would be an asymptote, right? A corner or cusp would be where those tangent lines don't agree, right? One's going one way, the other's going the other, and we need to have it going the same direction. Okay? All right, so we have a little 2-minute challenge here dealing with critical points. Okay? 19 is a sketch. Let's get a sketch. Agree on a sketch at your table. 23, what do we have to do here to take the derivative? We have to do what sort of thing? One of those things, yes, so whatever it's called. Awesome. A power rule, and what is between these two? So it's a product rule. Okay, so 2 minutes, go. With your tables. So sketch and product rule. Are you totally out, dead out? No juice with water?
I have 1%.
How far you think? Because you could touch water.
Just remember to log out. So we're about a minute into it.
You're doing something.
Oh, you are.
Yeah.
You're doing something.
I'm talking to you.
Doing I agree. You should be doing.
Okay.
Which means you should be taking notes.
Which means there's only one zero.
We're doing this problem. Doing that problem.
It gave me 3 points.
So here's sketch.
The relative max.
I'm fine.
I said what should be. And then a relative minimum at 1. I said what was 4.
Relative max.
And then a relative maximum of 5.
Relative min.
Yes, it only goes to the x-axis.
You should get a picture there.
23. This one you have to do math.
Okay, we got 30 seconds left. Andrews?
Oh, no. Why?
Continue it on forever and ever. It's calling
When you said how many zeros does it have, are you talking about how many derivatives of zeros? Or how many times does it cross the x-axis?
That's a zero. A zero is where it crosses the x-axis.
Why is it not one?
Answer?
Wait, I don't.
Oh.
Nope. Nope. Yes, I figured that out after you said you. Okay,
It starts off with
so pictures are really important, right? So let's take a look at this. Polynomial p of x has a relative maximum at -2, 4. Relative maximum means what? Hill or valley?
hill.
Hill. Okay? Has a relative minimum at 1, 1. Wow, that was not what I wanted to do. There we go. Okay? So this is what I do, ladies and gentlemen. Stop texting. Thank you. You're talking in the, okay, stop talking on the phone. Okay, so relative maximum, right? Little hill. Relative minimum, little valley, right? And it says no other critical points, no other hills, no other valleys, no other.
5, 7.
Oh yeah, I forgot the last one. No other hills, no other valleys, no other cusps, corners, and it has a maximum at 5, 7. Wait, 2, 3, 4, 5, 4, 6, 7. Maximum. Okay? How many got that far? Or at least knowing that, go, oh, I could do that. Now let's connect them, right? We know this is nice and smooth because there's no other hills or valleys or anything. We know this is nice and smooth. Okay, but this is a polynomial, which means what has to happen here and what has to happen here. Continues forever, right? It's curved. I drew it kind of straight. Continues forever. Zeros. Zeros mean what? Crosses x-axis. Where does it cross the x-axis? 2 times. Okay? How many critical points? So what do we have to do to find critical points? You gotta do the product rule, which means you have to take the derivative and find where it's what? 0. Ready for the derivative? What's the derivative of this first thing? Okay, yep. 5x plus 2 to the 4th. And since I took the derivative of the first, I leave the second alone, right? Okay, now leave the first alone. What's the derivative of this piece? 4x minus 3 cubed. Okay. And now, really, we've done the calculus. We gotta do some algebra though, to see how many, what do you think it is? 1, 2, 3, 4, 5, or 9? Okay, somebody wants to say 5. How many want to say 2 because you see 2 things in brackets? Okay, so you know what I mean? We have this, because when we're finding zeros, we're usually doing, something in bracket equals 0 or something else in bracket equals 0. Okay, so what we have to do though is we know that when we're finding zeros that way, they all have to be multiplied together, and we've got a plus sign in here. So let's try factoring out common factors in these 2 terms. Does each one of these terms have a 5? Coefficient 5? No. Does each one of these terms have an x plus 2? How many can we factor out? This one's got 4, this one's got 5. You can factor out 4, right? Okay. Do both these terms have an x minus 3? How many can we factor out? We've got to the 4th power here, to the 3rd power here, we can factor out 3. What's left? Or let me ask the question this way. Is there stuff left? Right, there is, right? There's at least what left here? A 5 and maybe some other stuff, right? How many can tell what the answer is at this point? Is it 2? Is it 5? It's not. Anybody want to venture a guess? It's not 2, it's not 5. Who said that? It's 3. How do you know it's 3 at this point? Did you know that? Oh, well, hey, you know, this is a nice thing about multiple choice, is sometimes those guesses are really educated. You know what I mean? When we're talking about, did you hear what Tyler just said? Isn't it because there's 3 things multiplied together? Here's something, and here's something. You got 3 things multiplied together, one of them's got to be 0, right? Because the derivative has to be equal to 0. So it's got to be this. Do we care what this is at this point? I don't. Sorry. I don't, seriously, because it's a multiple choice question. It's obvious that either this has got to be 0, this has got to be 0, or this has got to be 0. I just don't care what it is, because they're not asking me to find it. If you really, really want to know, it's this. It's that. And we could simplify it, but I don't care. How are we doing? Okay? Yeah. Uh-huh. Yeah. Well, but, okay, this is a good question. So if we listen up here, what Carly's saying is this is x plus 2 to the 4th power. Doesn't that mean there's 4 critical points? And anytime you have a repeated root, what that means graphically is that at -2, we touch. That's what repeated roots mean. We don't go through, we touch and go back up, or we touch and go back down. So the exponent is telling us that it's repeated, so that we don't, the exponent tells us, so this power of 4 and this power of 3 tells us we touch the x-axis and then bounce back away from it. So we don't go through. Like, for instance, like going through like this. Like x plus 2 times x plus 2. But would you get another unique answer? If you said x plus 2 equals 0, you get an answer of -2, right? If you set the next x plus 2 equal to 0, you'd still get -2. So it's not a different answer. It doesn't lead to another solution. Does that make sense? Okay. So like for instance, we would take this and we'd say x plus 2 to the 4th power equals 0. Right? We take the 4th root of this and the 4th root of this, so that ends up being x plus 2 equals 0. So it only gives you one unique critical point. Okay? Okay, so for today we're going to talk about something called the mean value theorem. And we're going to look at that graphically, and we're going to look at that analytically. In other words, using algebra. Okay? And we're going to take that then, and we're going to use that to talk about increasing and decreasing functions. I think you might have just a good conceptual knowledge of that. Okay? And then we're spending today and tomorrow doing this. So questions about that? Okay. So, first question, what does mean mean? Average. Awesome. Mean is another word for average or average value. Okay? So when we talk about graphically, when we talk about average value, we're talking about an average rate of change. Okay? We're talking about an average rate of change. Do we remember graphically what an average rate of change is drawn as? Pardon me? Okay, I agree. And the line has to touch the function in how many spots? 2. Okay? We have to be able, when we talk about an average rate of change, we have to be able to have a beginning and an end. Okay, and we have to be able to have the straight line between those. So everything you see here in black are average rates of change. Do we remember what we call a line that touches a curve in 2 spots? A secant line. Oops. So, knowing that, you see just 4 examples here. And my question is to you, really quickly, just like 15 seconds in your group, can you draw a tangent line somewhere on this curve that has this same slope? In other words, has the same slope as the average rate of change. Okay? So let's just talk about the average rate of change here. What's the average rate of change here? 0, right? Horizontal line. What's the average rate of change here? Up 1 over 3. Okay? So our average rate of change here is up 1, right 3. Our average rate of change here is 0. What's our average rate of change here? What's our average rate of change here? Okay. So I'm going to call that -1. Does that make sense? Down 3, right 3, down 3, right 3. Okay, so really quickly at your tables, can you draw a tangent line that has that same slope somewhere between those 2 points, somewhere in this interval for each one? Go ahead and try to do that in just a real quick 15 seconds. So maybe about 15 more seconds. Can you quickly just sketch them? Tangent to the curve, exactly. So, yeah, just a real quick, it's just an estimate. We're looking for graphical representations here. So, to the best of your ability, some people are drawing that line and moving that line. That's an awesome idea. They're just kind of seeing it, kind of drawing it right on top of the black line and then sliding it in their ability to where they think it looks best. And, judging from what I'm seeing lots of really good answers. Yeah. Yeah, exactly. Okay, so can we nail down this location pretty well on the upside down parabola? Taylor's saying yes. Where is that point of tangency that's got the same slope? What x value? 1. Okay, awesome. So let's see what color I want to use now. I'll go, let's go orange. This is just one of my faves. Okay, so so right there, we also have a slope equal to 0. What is the slope of the tangent line called? We got a couple of different words for it. Slope of the tangent line, we can call it that. We can also call it the derivative. We can also call it it's a rate of change. What kind of rate of change is it? Instantaneous rate of change. So we're talking about now our instantaneous rate of change. And it looks like it's about x equals for this one. Try to write down the right answer. It looks like for this one, it occurs at about x equals 1. Instantaneous rate of change. How about here? Where is it? About -1, right? We're going to draw something that looks like that. And then we're going to kind of, I saw people doing this, right? Sliding it in Notability and saying, it's there-ish. Looks about there, you know, -1/2-ish. That's harder to find specifically. This is when we need to kind of go away from a graphical solution and more towards an analytical. How about here? Are derivatives defined at the cusp of the corner? Okay, so it does not exist. It does not exist because we don't have a defined derivative at that location. What about here? Right where it starts curving down. So about there-ish. Okay, that looks like it's pretty close to x equals 0, but I'm not completely sure. So we have a situation where we've got two of them we really definitively know. This one, it's close to half, -1/2, we're not sure. This one, close to x equals 0, but how can we know for sure? Okay, and we know that the slope here, though, is definitely -1 because we matched it with this slope. This slope is definitely 1/3. We matched it with this slope. That was the criteria. So when we talk about identifying a mean value, what we're saying is that what is this an expression of? That represents what sort of value? And this represents what sort of value? Okay, the first one's a derivative. And another word for derivative is awesome. Instantaneous. That will help you with the next term. Okay, the instantaneous rate of change is the derivative. What's this? It is a rate of change. What kind of rate of change is it? Nope. Average. Okay, this is the 2 points, right? This is our A comma f of A and our B comma f of B. That's our rise over run. Those are our 2 points on the curve that make our secant line. Okay, so what is this saying? Yep. Okay, that the instantaneous rate of change is equal to the average rate of change. Okay, and so now we've got a way where we can analytically figure out in those 2 examples that we kind of could get close. but couldn't get an exact answer for it graphically. So what, because we know the average rates of change, right? One was 1 over 3 and the other one was -1. So we know the average rates of change. We're just going to find the derivatives and set it equal to the average rate of change. And so that's kind of what this page says. Okay, our instantaneous rate of change equals our average or our mean rate of change. And so when we look at this really closely and look at the verbiage really, we're saying, first of all, f of x has to be continuous. Were all those functions above continuous? Did we have closed intervals? We did, right? We had square brackets on our interval notation. We had closed dots there. Were all of those functions differentiable at every point? No. Okay. Tim says no. Which one was not differentiable at every point? Yeah, that's a corner, right? Two lines coming together is a corner. Two curves forming a sharp point is a cusp. Okay, so this is not differentiable at every point. That's why this had no average or instantaneous rate of change. Okay, so that type of graph isn't applicable for the mean value theorem. So we're going to take a look at that last graph. Here's that last graph. It's actually that function. Okay, and so we're going to find the derivative of that. Okay, so what's our derivative? (3x squared minus 6x minus 1). Okay, there's our derivative. Okay, now what is my average rate of change? What is my rise over run? Okay, my average rate of change, in other words, my rise over run, my FB minus FA over B minus A equals -1. So I want to know where the slope, the tangent line on that curve is equal to what? I want to know where this derivative is equal to -1. So I'm going to go ahead and say, well, where is this derivative? 3x squared minus 6x minus 1 equal to -1. I want to solve that. So how do I solve that? How do you want to solve this? Probably involves some sort of factoring, right? We have an x squared term. So the first step of factoring is to do what? Yeah, let's get one side equal to 0. And that's how we can do that. Add 1 to each side. Okay, so we've got 3x squared minus 6x. Oh, that's nice and convenient. And then Tim says factor out an x. Oh, we could have. I'll go with just an x. So what is this telling us? Okay, so x equals 0 and 3x minus 6 equals 0. So at x equals 0, we should have something with a slope of -1. And what about 3x? What about 3x minus 6? What is that telling us? Okay, so x is equal to what? Regular 2, right. X is equal to regular 2. I did 2 steps there, right? I added 6 and then divided by 3. Where is x equal to regular 2? OMG. It's at one of the endpoints in the interval. Is that okay?
Yes.
It happens. Okay, because we're talking about the closed interval, which includes the endpoints. So we could just happen to have that one point as a point of tangency. We just happen to pick it at the end of its interval. That's okay. You okay? Okay, just Andy? Okay, so and when we're talking about the mean value theorem, we're just saying really, I have this average value for my slope, and I want my derivative to match it. And it's going to happen somewhere in that interval, as long as those criteria are met. I have a continuous function, I have a differentiable function. We're good to go. Somewhere along that line, not to be funny, somewhere in that interval there's gonna be some sort of tangent line that matches my rise over run. Better? Okay. So down below is kind of a physical application. It's saying, here's a position function, and we know that the average rate of change in position is called what? Velocity. So somewhere in these first 8 seconds here, if my average velocity is 44 feet per second, which is about 30 miles an hour, somewhere in that first 8 seconds, I had to have been going 30 miles an hour. Does that make sense? So if you think about accelerating on the on-ramp, starting at 0, accelerating up to 60 miles per hour, if you go from 0 to 60, you might average 30. Does your speedometer sometime, as you're accelerating on that ramp, go through 30? Does it have to? I can't jump over it. So your speedometer is representing an instantaneous rate of change. It's what you're driving at that instant. So somewhere the speedometer is going to have to read that value, that average value. Okay? Okay, quick activity at your table here. We're talking about here increasing and decreasing functions. So I have this function x cubed minus 4x. And I just want you to highlight those 3 things. Pink, where the function is increasing, where's that mean? What does increasing mean? Increasing means what? Increasing means getting bigger. Good. Decreasing means, yay. Now that we got that, really quickly, like less than a minute. Go ahead and highlight that. Pink, green, and blue. Awesome, awesome. Looking good. I agree. Where are my blue dots? Okay, hills and valleys. Okay, where's my pink? And I agree. In between. Okay? So increasing, like you said, means getting larger. Decreasing means getting smaller. So we're just talking about what direction are we moving vertically. Okay, let's look at this from the perspective of the derivative. Where would be an easy place to calculate the derivative? Okay, at the blue dots. What's true about the derivative at the blue dots? Okay. Okay. Now, let's talk about the derivative, the value of the derivative in the pink area. What's the value of the derivative in the pink area? I agree, it changes. It changes in value, right? But tell me something in general. I could. I agree. Like if I drew the tangent line here, tell me about these tangent lines. What do they all have in common? They're pink. Awesome. Super sweet. All these tangent lines, what kind of slope do they have? They all have positive slope. So if a function is increasing, what's true? Ladies and gentlemen, positive slope. What about these decreasing functions? What kind of slope do they have? Negative. Okay, those decreasing functions have negative slope. So when it comes to finding out from a derivative perspective, whether a function's increasing or decreasing, you just have to look at what? Sine of the slope. Exactly. So in order to do that, we have just these analytical ways to find where functions are increasing and decreasing. So we can look at the function itself, and if we have a graph, we can physically see that the values are getting bigger or smaller. Or we can look at the derivative if we don't have a picture of the function itself, and say where is the derivative, positive or negative. So that's really what this definition and the corollary are saying. And so a lot of times it's more convenient to look at the derivative. It just is. So if we look at this function, we know the blue dots are the derivative. Let's take a look at that derivative. So x cubed minus 4x. Yeah. Okay, x cubed minus 4x. What's the derivative? Okay, so how do we find those critical points? Equals 0, right? Critical points are 0 slope. So what are those critical points? How many critical points do I have? Where do they come from? Plus or minus? Okay, so we have these critical points at two locations. Okay, a little over -1 and a little over +1. So we can draw a chart then. So this represents -2/√3, and this represents 2/√3. And so the question is for this interval, in other words, for this But for this spot in the function, what is that function doing? As we travel in this interval, it's increasing. And so we can test that by doing this. We know the derivative is 3x squared minus 4. So what if we tested it by putting in -2? So what if we tested it by putting in -2? Okay. If we put in -2, then we have, I guess I can make this box big enough. We've got 12 minus 4, which is 8. Is the derivative positive or negative? The derivative is positive, so this must be increasing. What happens when we plug in 0? We put 0 in here, we get -4. Is the derivative positive or negative? Negative, so we are decreasing. What if we try 2 here? Yeah, we have some symmetry here. We get a positive derivative, we have an increasing function there as well. I just realized this is a typo. I should say the behavior of f, not f prime. Okay? So we can tell by just finding those critical points and then testing something on each side of the critical point. And just saying, okay, is the derivative positive or negative? And so from analytically without the graph, right, just using algebra and taking derivatives, we can determine whether our function is increasing and decreasing. So questions there. Okay, so mean value theorem, define points of tangency with same slope, and then using critical points to find increasing and decreasing functions. Okay, are the 2 things we're focusing on. All right. Tomorrow it'll just be a small wrap up, and then I have a short survey for you from last week's summative, and then we'll go over, spend a little time just kind of giving you the summative back and hitting some of the highlights there.